Assume the truth of the distributive law, Appendix A, F3, and use the recursive definition of summation together with mathematical induction to prove the generalized distributive law that for every positive integer n, if a sub 1, a sub 2, up to a sub n, and c are real numbers, then this equation holds. Now here's F3, which is the distributive law. Now I really want to emphasize what the distributive law says here. This says that if we have a times parentheses b plus c, we can essentially distribute the a to both terms to get ab plus ac. Now I really want to emphasize that the distributive law can only be applied to two terms. So it might be tempting to take this c and essentially distribute it to each a sub I, starting at a sub 1, and eventually you get the sum of c times a sub I for each I between 1 through n. But that's not how we can apply the distributive law. The distributive law only applies if you're distributing a factor a to two terms b and c. So we have to be careful about distributing factors to multiple terms. And so this is where we have to use mathematical induction to get around this issue. Now this right here is going to be p of n. And we're going to prove that p of n is true for every integer n greater than or equal to 1. We'll start with the base case, which is when n equals 1. So I'm just going to rewrite this equation here, but I'm replacing n with 1. So this is the statement p of 1. Now I'm going to put a question mark here because we want to prove that this is true. To prove this, we're going to evaluate both sides of this equation separately. Starting with the left-hand side, we have the summation from I equals 1 to 1 of c times a sub I. Now, since the index variable starts at 1 and ends at 1, then this is just one term, c times a sub 1. Now that's a simplification of this left-hand side here. Now let's evaluate the right-hand side. This is just going to be c times a sub 1, and we could drop the parentheses here to get c times a sub 1. And in both cases, we get c times a sub 1, and so this equation must be true. Now let's do the inductive step. Let k be an arbitrary fixed positive integer and assume that p of k is true. So p of k is our inductive hypothesis, which is a statement that these two things are equal to each other, that the summation from I equals 1 to k of c times a sub I equals c times the summation from I equals 1 to k of a sub I. We want to show that the summation from I equals 1 to k plus 1 of c times a sub I equals c times the summation from I equals 1 to k plus 1 of a sub I. Now to show this, we're going to actually start with the right-hand side, and we're going to do a couple things with this. Now, what I'm going to do first is I'm going to pull out the last term from this series. And you can check out my last video, and you can check out one of my previous videos that discusses this exact topic on how to pull the last term out from a series. But just to remind you, I'm going to show you explicitly how to do this by writing this series in expanded form. If we iterate the index variable I from 1 to k plus 1, this is just a sub 1 plus a sub 2 plus a sub 3 plus plus a sub k plus 1. That would be the last term. But when we're pulling out the last term, what I like to do is I like to write the last two terms, which the second to last term here would be a sub k, and then the last term would be a sub k plus 1. Now the way we pull out this last term is we regroup together the first k terms into a new summation with a different index. So the way we pull out the k plus 1th term is we regroup the first k terms together into a new summation. So this will be c times the summation from I equals 1 to k of a sub I. But then totally separate from that, we have plus a sub k plus 1. That's the last term of that series. We've essentially pulled it out of the summation. Now here's the key. We're allowed to use the distributive law here. Just to remind you, the distributive law says that A times B plus C equals AB plus AC. This only works if we only have two terms. In this instance here, we have C, which can be distributed to these two terms here if we consider this summation to be a term within itself. And the way we do that is we can imagine those parentheses around the summation to show that this is just one object. And we're distributing C to this one object, and then the other object, A sub k plus 1. So by the distributive law, which is labeled as F3, this is C times the summation from I equals 1 to k of A sub I, and then totally separately plus C times A sub k plus 1. We've distributed the C to both terms using the distributive law. Now let's go to our inductive hypothesis here. Our inductive hypothesis tells us what C times parentheses the summation from I equals 1 to k of A sub I is. According to the inductive hypothesis, we can rewrite that as the summation from I equals 1 to k of C times A sub I. So let's apply the inductive hypothesis here. This is the summation from I equals 1 to k of C times A sub I. That's by the inductive hypothesis. And then we still have this plus C times A sub k plus 1. Now the way we finish this proof, the way we finally get to the left-hand side of what we wanted to show, keep in mind we started with the right-hand side of this P of k plus 1, and we've done some things so far using the distributive law, and we've applied the inductive hypothesis, which, just a reminder, whenever you apply the inductive hypothesis, you need to remind the reader that you're applying the inductive hypothesis. And now we have this expression. The next thing we have to do is we have to absorb this k plus 1th term into this series. Essentially, we're doing exactly the opposite of what we did earlier. Earlier, we pulled out the last term. Now we're going to be reabsorbing this last term into this series. But to show you how we do this explicitly, I have some previous videos discussing this, but the trick to understanding what's going on here is to expand this series. In expanded form, we can iterate the index variable from I equals 1 to k and write C times A sub 1 plus C times A sub 2 plus dot 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 plus C times A sub k. Now we have this plus C times A sub k plus 1. And then we can rewrite this entire expanded form as one summation. The summation from I equals 1 to k plus 1 of C times A sub I. And that is the left-hand side of what we wanted to show. We started with the right-hand side of P of k plus 1. And we did some stuff using the distributive law carefully. And then we applied the inductive hypothesis. And then we wrote everything in expanded form and rewrote everything into one summation, which is the same as the left-hand side of what we wanted to show here. And so ultimately, the left-hand side of P of k plus 1 equals the right-hand side of P of k plus 1. And so P of k plus 1 is true. And so therefore, by mathematical induction, P of n is true for all positive integers n. Thanks, everyone, and I'll see you in the next video.